This presentation explores the application of swarm algorithms for autonomous exploration of unknown areas within the ROS2 framework. We will discuss how swarm robotics enables efficient real-time exploration, obstacle avoidance, and adaptation to dynamic environments without prior knowledge of the terrain. This work was authored by Alexander Bessonov, Stanislav Piskunov, Oleg Rudenko, and myself, Sofia Rutska. I will be presenting this project today. Swarm robotics enables multiple robots to collaborate using decentralized control for tasks like exploration, mapping, and search operations. In these works were developed and tested a swarm system that adapts to dynamic environments, integrating the multi-agent B algorithm with enhanced sensor for improved coordination and obstacle detection. Our experiments evaluated the system's scalability, stability, and effectiveness in unknown terrain, confirming its potential for disaster response, environmental monitoring, and industrial applications. Among the main algorithms, the particle swarm optimization algorithm, ant colony algorithm, and bee algorithm were studied. It was necessary to select an algorithm that should prioritize space exploration in real time without prior knowledge of the map, efficiently distribute robots to avoid crowdings, and adapt to obstacles and dynamics environments for efficient navigation and coverage. The particle swarm optimization algorithm is based on a social psychological behavioral model of a crowd. This algorithm capable of solving non-linear and multi-dimensional problems, typically achieving good solutions very quickly, while requiring minimal parameterization. Ant colony optimization is inspired by the foraging behavior of ants and is used to solve combinatorial optimization problems. Continuous ant colony optimization is an improved version designed for continuous space, where robots move freely along coordinates and update a virtual pheromone, unlike the original method, which operates with predefined nodes. The B algorithm is a metaheuristic optimization algorithm inspired by foraging behavior of real bees. It simulates the work of scouts searching for new sources of nectar and worker bees in satisfying their search in the most promising areas. Multi-agent systems is inspired by bee behavior, have a unique ability to adapt to changes in the environment, and efficiently solve resources allocation problems. The image shows a graphical visualization of the frame tree in the ROS2 system created using TF2 and the View Frames tool. The map node is a global coordinate system linked to ODOM, odometric system, that tracks the robot's position. It connected to base footprint, the robot's base point, and then to base link, the main frame linking all other components. SLAM enables a robot to create a map of an unknown environment while checking its position within the map in real time. SLAM becomes indispensable in environments where there is no pre-prepared map of the terrain or the position of the device is unknown, making it a versatile tool for a variety of tasks. SLAM system can use different types of sensor to collect data about the environment like laser, acoustic, or visual. The range flow 2D odometry method is used to estimate robot odometry based on a successive comparison of laser scans. This approach helps to improve the accuracy and stability of odometry estimation, especially in dynamics and complex environments where traditional methods may have limitations. Navigation 2, Nav2, is a powerful navigation stack for ROS2, designed for autonomous movement of mobile robots. Nav2 is based on a modular principle where each component is responsible for a specific part of the navigation process. The system processes a robot's current position, map data, and target destination to generate a safe and efficient movement plan. The NAV2 system is composed of multiple ROS components whose interactions are illustrated in the diagram. The system uses behavior trees instead of finite state machines for navigation, calling NAV2 recoveries, planner, and controller servers that host algorithm plugins. Several experiments were conducted with the robot system on different types of maps, scaling the number of robots used to build a map of an unknown area. Experiment 1 involves the use of the multi-agent B algorithm, which allows scout robots to be used to cover a larger area for exploration. Since LiDAR does not distinguish between robots and normal obstacles, robots may mistakenly see walls or other objects as other members of the swarm, which can sometimes alter their assessment of the area and cause one robot that has separated from the group to be unable to return to the swarm without outside interaction. Three types of maps were used for experiment 1 and 2, a rectangular box with obstacles inside, a corridor type area, and the area around a large object. In all three types of maps, the robots had the same amount of time to cover as much territory as possible and return to the starting point. Experiment 2 used a similar algorithm as the first experiment, but also created a dynamic environment in which the robots had to cover the territory, taking into account the possible emergence of new obstacles. Also, in a dynamic environment, a different number of robots in a swarm was tested for a clear example of the scalability of the system. For this situation, the same types of maps were used that were used in a previous experiment. The current setup of the robots, different from the previous one, is that new sensor and cameras were used, which allowed them to accurately determine the position of swarm members in a dynamically changing environment and avoid already marked and explored territories. In the result, this study presents a swarm intelligence-based system for autonomous exploration, localization, and mapping. The research focuses on optimizing robotic control strategies for ground robots in unknown environments. The developed system has potential applications in search and rescue operations, dangerous material detection, and environmental monitoring, demonstrating the broader impact of swarm robotics in real-world scenarios. The multi-agent B algorithm expands exploration, while added sensor improves stability despite LiDAR limits and higher complexity. Results indicate that a larger swarm size improves system resilience as more robots successfully return to base in dynamic conditions, highlighting the system's scalability. Overall, the experiments confirmed the effectiveness of developed methods for swarm-based exploration in both static and dynamic environments. Future improvements should focus on enhancing sensor fusion, optimizing synchronization, and increasing autonomy to better handle unpredictable conditions. Thank you for your time.